Sotirios, welcome. Appreciate you being here.
Thanks for the invite.
This is a pretty special day on A Penny for Your Thoughts. Andrew, we've hinted to our listeners and to our viewers that we've got some cool stuff in the works. And what you'll notice right away is we're in a new studio, so we're super excited about that. Sotirios, we're grateful that you get to be our first guest. Andrew, I was going to joke that we needed to call Dr. Know-It-All, and we should have had him come and introduce it.
Darren Mueller.
Darren Mueller was our first, one of our first guests on the show, but just really appreciate you being here with us today, and got some really exciting stuff to cover, some of the work that you guys have been doing. But Andrew writes our script, as everybody knows, but I'm going to go off script for a second because this feels like a milestone for us. And so on Tuesday, we had a group of the science-bound students from Iowa State, which to our audience, if you don't know about Science Bound at Iowa State, it's an incredible program that starts youth in science. If they complete the program and go into sciences at Iowa State, they can actually get a full ride. Check that program out. It's incredible. Had the opportunity to speak to them, and what I challenge them is no matter what the rest of the world tells you, find something that you're so passionate about that it eats at you at night, and it's the first thing you think about when you wake up, right? Because your salary, the benefits, all the things the world cares about, that's what will drive you. And I'm thinking about that as we're preparing to come here today and do this. And I just thought, Andrew, I wouldn't be here doing this if it wasn't for you finding your passion. This idea was born out of you sharing your passion with other people. And so it's just hard to sit here and see how far we've come and not just feel incredibly grateful for that. So
Yeah.
I was looking at 8th grade students looking back at me having this conversation, and I'm like, I'm sure they're like, what's this guy even talking about? But I have these moments where you and I getting to do that has had a huge impact on my life, and I'm super appreciative of that. So
That's almost 100th episode stuff we should have covered then.
Yeah.
I would agree. It's being able to talk to these professors and bring good science out there to people and help growers, other agronomists, even other professors think differently, refine their research, build on what growers are wanting answers to. It's been tremendously impactful on my career. I love, coming from the university, teaching an agronomy class, being able to help get some of this science out there to people is very fun. And I feel every time we meet with professors, I feel that it's a privilege.
Yeah.
And getting to do it with you again. This should have been on the 100th episode, right? So we're celebrating. So no,
I didn't feel that affectionate towards you 3 episodes ago. It's just now. So no, I just it's a really cool opportunity, and it's neat to be here today. So we got that out of the way. I'd also like the record to show I say nice things about Andrew, and there's part of my script that's covered up. So I'm sure something dumb is coming later in the episode, but we'll get to that in a minute. But Andrew, as we start today, go ahead, introduce our guest and kind of give us a scope of what we're going to talk about today.
Yeah, this is. We have a whole month and a half, 2 months dedicated to nitrogen, and we're lucky to have Dr. Sotirios Archontoulis on here from Iowa State, and he's done some phenomenal research looking at hybrid interaction, nitrogen uptake, nitrogen use in kind of old era hybrids and modern era hybrids. And, just thinking about some of his research, looking at mineralization rates, helping, Dr. Mike Castellano with, some of the nitrogen initiative that we got going on in Iowa. It's just looking at 2026, even 2025 in central Iowa, it's just a tremendous opportunity and perfect timing to have these conversations around not just nitrogen, but how can we learn and understand from what based on your research looking at modern hybrids, how does that impact what growers do with nitrogen, right? So there's so many interactions with that. So, we're going to discuss some of these learnings from this research, looking at old hybrids versus new hybrids, and then how can we use that to help growers be more productive, increase nutrient use efficiency, all that fun stuff. So, going to be some phenomenal conversation.
Yeah, it'll be good. So, Sotirios, as we get started today, got 2 questions for you. To kind of kick our show off. So first and foremost, our audience knows this, but we break the episode into 2 parts. So science, we'll talk about the science, your research, what you learned. Then we'll discuss management. What does that mean for growers and advisors? But to begin, tell our audience a little bit about yourself and how did you end up in the position you're in at Iowa State, a little bit about your background.
Yeah, sure. Thanks, Son. First of all, honored to be here in the 100 episode. I like this number, so pretty good to be here. Professor of agronomy with Iowa State University since 2012. Before that, I was in the Netherlands, 7 years at Wageningen University. Over there, I did my master's and PhD in crop science and crop modeling. Before that, I was in Greece. I did my bachelor in agriculture, and before I go to the university, I was working with my dad in the farm.
Okay.
We were growing cotton. He still grows cotton, and this is how I learned the basics. And to tell you a story there, I was asking lots of questions. I was very, very curious. And this is how it started the science for me. It was impossible by being in the field all the time to get all the answers. I need to figure out something more sophisticated. And this is what it get me into computer simulation models. And part of my work, what I do with Iowa State University, is to integrate the science, the crops, the soils, the weather, the management, the hybrids that we're going to talk a lot today, and see what is the outputs every year and how one year affects the other one. That's a little bit of a description about me.
Yeah.
The immediate takeaway I have from that, I've been listening to some other podcasts, and a lot of the themes from some of the most exceptional people is this concept of staying curious, right? No matter what else changes, curiosity is what drives us to continue to ask questions and learn. And so I'm jotting down notes. That's one of my takeaways. One of the things we like to start our show with before we dive into your research is when you think about the landscape of agriculture today, what has you really excited?
You know what? What excites me with agriculture and crop production in general is that every year is a unique year. Last year, we had to deal with excessive rain in July. This year, in central Iowa, we had a couple of episodes of lots of rain. We had a weekend full of rain, and then a week nothing, 2 weeks nothing. Every year is something different. And the job of an agronomist is to explain the why. And that's exciting, right? You try to figure out what's the problem, what we should do in the future to mitigate this problem. So it's pretty exciting. Also, the prediction aspect of it, giving every year the challenges, what is going to be the yield. So it's the unknown, it's the uncertainty, trying to figure out the path and be right or directionally correct. It's pretty exciting. This is what I love the most about science.
Did you predict, what was that, about a month ago, 12 and a half inches of rain in 36 hours? Were the models very close on that one?
I stay away from weather prediction.
It's funny. I know I was Sean's agronomist, and still, him and his team still lean on me. They expect me to know everything and be able to predict everything.
So far as batting average, I don't know that he's making it to the Hall of Fame, but occasionally he gets one or two right. So, well, let's dive into this. It's exciting research, and so spend a little bit of time going over some of the research you've done, but maybe give us an overview, just a quick overview of kind of what you started out with, and then we're talking about old era versus new era hybrids. So maybe the scope of that, how many products were you looking at, that sort of thing?
Yeah, it was a big project. It was funded by the Foundation for Food and Agriculture Research and Bayer Crop Science. It was a 4-year project, involved Iowa State University, Purdue University, and Stanford Center for Plant Science. It was a big group of scientists, Tony Vine from Purdue, Chris Topp from Stanford, myself, Mike Castellano, Pat Snubble, Kendall Lamke from Iowa State University, and we had many students, many postdocs, and over the course of 4 years, more than 30 people involved in this project.
And the research was done in Nebraska, right?
The research was done all over the Corn Belt.
Okay.
Listen to that. We had 100 experiments.
Wow.
We were throwing around some big names right there, from Tony Vine to Kendall to you and Castellano.
It was a great project, and a great project makes it the good people that you have in the team.
Yeah.
So it was also a big project in terms of scale. We never ran before experiments to study the hybrids, the crop physiology at this scale, starting from Nebraska, dryland, all the way to Purdue, all the way to Indiana and Ohio, the very wet conditions. The scale would have been impossible without us collaborating with industry. We are pretty good in collecting data and doing the science, but we cannot operate at scale. So this partnership, it was really the key for the big success. Within an experiment, we had 40 hybrids.
40 hybrids. Okay.
Old hybrids from 80s all the way to modern hybrids 2020. And we also had 2 relative maturities. So if we multiply 2 relative maturities with 40 products, this makes a total of 80 hybrids.
That's a lot.
That's a lot.
What were the 2 RMs?
The first one, it was average 103,
Okay.
and it had products from 100 to 105.
Okay.
And the other one is 111, the average, and it ranged from 109 to 113.
Man, that's a lot. I mean, just doing research, that's a lot of, I'm picturing the amount of plots and all that stuff. And we haven't even gotten into data collection yet. That's where it really gets, that's where all that grad student help.
Oh, it was the human high throughput phenotyping.
Yeah.
The best of the best.
Yeah. So then the old era hybrids would be hybrids from 80s through.
We had the hybrids change every 5 years.
Okay.
So we had hybrids 1983, 85, 86, 87. So we were picking 5 hybrids every 5 years, every decade, basically.
Okay.
So, and the total.
What vintage would you be?
What
Are you in the 80s?
81.
81. Okay.
Yeah.
You'd have made the test.
I would have made the test. So then the newer hybrids, where did that start?
The new hybrid, it started 2015, 16, 17.
Okay. So pretty recent.
Yeah, pretty recent.
Man, I think some of those products you'd actually still be out in the market.
Well, and so I'd ask you a question. This isn't on the list, I don't think, but do you classify a new era hybrid as something that changed in breeding or as just a period of time? Like, was there an event that caused you to declare something a new age hybrid versus an old age hybrid?
Yeah, so this is mostly because of when the hybrid is released on the market.
Yep.
So the year of hybrid release, it was the point that we were classifying a hybrid as old, as very, very old, as modern hybrid, or a little bit old.
Yeah. So the goal of this is to kind of learn about your science and research, and then in the management portion, take that. How can we use and understand that to impact how we think about and manage our nitrogen applications in the field? How many nitrogen, so across these old and new hybrids, how many nitrogen, different nitrogen parts, we'll say, did you look at?
In the first round of the ERA study, we had 2 nitrogen rates, a low rate around 40, and then a sufficient rate around 200, 210 pounds of nitrogen per acre.
Okay.
That was in the first round of experiment, because out of this big project, let me say that differently, generated a second project, which, guys, you have more interest on that. That was the first ERA nitrogen project.
Okay.
So on this one, we designed not 100, but close to 25, 30 experiments across the Corn Belt again. And we had old hybrids, 1980s to 2020. Then we had many modern hybrids. We had the tall corn, many hybrids, more than 20, 40 hybrids. And then we had the short corn, where we were studying this as well. The beauty of that experiment is that every hybrid at every location was tested at 5 nitrogen rates.
Wow.
0 to 300 at steps of 60.
Okay. How many nitrogen characteristics did you look at? I'm thinking it seems like we have 15 different ways to calculate nitrogen use efficiency. I made the joke with Castellano. I'm the simpleton. I like looking at nitrogen applied, bushels removed. Right. Keep it simple. How many nitrogen characteristics did you look at? You know, you have leaf concentration, you got stock concentration, you got overall content. You got it impacts root biomass, right? So how many different characteristics and traits did you look at on that corn plant?
A lot. Probably we hit the limit with what we did. But there are a lot, and pretty much we calculated everything. And there is some sort of correlation among all these indicators.
Big corn makes big yields, right?
That's true. Very true. But not always true.
True.
To your nitrogen use efficiency, I like to classify this into three main categories. The one that you mentioned, I like this a lot, yield versus applied fertilizer. I call this the agronomic efficiency. And then the second one, which I have a particular, I like it the most because I'm a crop scientist, is the physiological efficiency. How much nitrogen can the plant take up? The nitrogen uptake versus the nitrogen supply.
Yeah. So to get that, you're measuring plant parts overall. I mean, all the nitrogen in the plant, grain, all that.
We measure grain, we measure stover, and we measure the concentration of each tissue.
Okay.
How much nitrogen is in the grain, how much nitrogen is in the stover. And then we do all the math and calculate the total N uptake, and then the relation between yield and N uptake.
We've kind of struggled through this debate as we talk about side dress and all the different forms of nitrogen. Ultimately, the grower cares about what did I spend and what was my output, right? I mean, that's the conversion that ultimately matters on the balance sheet. But the challenge to me seems to be yield potentials generated by that whole algorithm, right? Like how much should I take? How much gets converted? So those are challenging conversations to have at the field because sometimes you can have a plant that has, the plant can be very efficient in capturing nitrogen, but other variables can dictate whether or not that turns into grain that we carry off of the field. So those are, that'll be interesting data to try and understand.
Absolutely. To me, the number one goal, by far, have the plant take up as much nitrogen as possible. Increase the N uptake.
So kind of leading into that, Sean kind of brought this up. We have these tricky conversations around yield and applied N and the impact that Mother Nature has, right? You tell me what Mother Nature is going to do. I'll give you the best nitrogen plan and the best form to apply, right? How does, thinking about your different nitrogen rates, how does the timing of application impact some of those characteristics or even the rate, right? You get this interaction of rate, but you also have the impact of timing. If we would have had all of our fall applied N in these trials in the fall, depending on
and can you clarify also? So you said 5 different rates in 60-pound increments, 0 to 300. Were those all one application? Okay, so all one application, and that application was what?
It was before planting.
Okay, so pre-plant.
It was from 2 weeks to 4 weeks before planting. I don't remember exactly, but it was.
So spring applied nitrogen.
Yeah.
Okay.
And in what form?
It varied from Nebraska to Ohio.
Okay.
We use the most common by region.
Yeah.
Gotcha. Okay, that makes sense. Yep.
Okay. No, that's so. What is your thoughts on that? If we're looking at nitrogen concentration and maybe nitrogen use efficiency in these new hybrids compared to old hybrids, how does that play into maybe what you're looking at in the results?
Yeah. So that's a great question and sounds simple, but it's very complicated answer.
Yeah.
I will do my best to give you a simple answer here. Maize breeding has changed the grain protein concentration. Changing grain protein concentration, you change the nitrogen. There is a straight relation there, one-to-one relation.
Meaning how much protein's in the grain impacts nitrogen uptake?
It is protein to nitrogen. It's a simple conversion with a factor of 6.25.
Oh, gotcha. Yeah, the amount of nitrogen needed to produce the protein in the grain. Yeah.
Exactly.
Yep.
So maize breeding over the time has decreased the protein concentration. On the other side, has increased the starch concentration.
Protein down, starch up, therefore less nitrogen is required.
It's required,
Okay.
but here is the trick. Now I'm gonna complicate things.
Okay.
So this is one direction. So this is less nitrogen required. On the other side, breeding has increased the whole canopy photosynthesis. So the plants can capture more CO2 and convert it into biomass. So more biomass requires more nitrogen. So you have one driving force and you have another driving force. The net result of these two is the nitrogen is going up, the nitrogen requirement.
Interesting.
So
So can I restate that to make sure I understand? So the nitrogen it takes to create today's biomass has increased, but the nitrogen it takes to create the starch or the yield has decreased, resulting in a net increase in need for nitrogen.
That is correct. That is
Interesting.
correct.
Okay.
And is that just a hybrid genetic thing, or is that, thinking about yields have gone up? Obviously, we need more nitrogen, right?
That's the explanation. Higher yield, you have more biomass built up there, and of course you need more nitrogen, fertilizer or from another source to satisfy this, to build dry matter. You need to have nitrogen.
Right.
It's impossible photosynthesis to operate without nitrogen. Nitrogen must come from somewhere.
You mentioned that. I wanted to touch on that, build on that. So you mentioned we've improved photosynthesis through breeding.
Mm-hmm.
So when you look at carbon flock and just the carbon intake converting that. So when we look at older hybrids compared to the newer hybrids, we've improved photosynthesis to the point where we're capturing more carbon and converting that into dry matter.
That is correct.
Okay.
The conversion efficiency of sunlight has increased a lot. Now, this is not something like, this is a trait. This is a complex trait. This is the product of 10 individual traits. And if I start naming those, there are many. It's the partitioning coefficients between leaves and stems, it's the canopy architecture, it's the leaf angle, it's the distribution of nitrogen within the leaves in the canopy, it's the light distribution, it's how fast the leaves are appearing, and so many other things. Every single trait contributes a little bit, and then you build up on those and you see a big increase, especially when you compare old hybrids, 80s, with modern hybrids, 2020. There you see a clear difference.
That's interesting.
And let me, Son, I'm going to make things a little bit more complicated.
We need like Westgate sitting here to help us
Breeding has changed the hybrids.
Yep.
But at the same time, we have the management. And I want to go back to grain nitrogen concentration. Breeding has changed that. Nitrogen fertilizer application rate has a big effect on the grain nitrogen concentration. The other agronomic factor with really big effect on the grain nitrogen concentration is the plant population. Are you using 32 or 42,000 plants per acre?
Really the question around, obviously we've changed row spacing in that 40 years. We've changed population relatively significantly in that 40 years. So how does that get accounted for as you're doing this research?
Yeah, that's a great point. In the very first ERA study that we ran with the 100 site years, we had about 8 site years where we had 2 treatments. Okay. One was fixed density and changing only the hybrids. And the other treatment was changing the hybrids and at the same time follow the plant population increase. So we grew the old hybrids at the population of 1980s, the 1990s hybrids at that population, and so on. Yeah. So we had 2 treatments, one flat, one increasing. We measured both treatments, and by difference, we were able to separate the contribution of breeding by plant density.
I'm not sure that people that haven't been around this type of research understand the size of these trials. I mean, that's massive research.
That's absolutely true.
I know. I'm just thinking about even going back 10 or 15 years. You start planting some of these hybrids at 39,000, you're gonna have down corn by R2, R3.
Yeah.
I can only imagine planting an 80s era hybrid, what that would look like at 39,000. You know, we discussed the sunlight, and you mentioned kind of the above ground biomass and grain. You know, that was kind of perfectly leading in one of the questions. You know, we start talking about the harvest index. And so explain that to our audience and kind of what you guys looked at and found.
Harvest index is something we use a lot in agronomy among the scientists, but it is a simple ratio, how much grain you have divided with the total plant biomass. This ratio, it was considered for many years to be constant, fixed. This doesn't change. And what we learned from this study is that it has increased. Now, I will tell you the numbers. From 0.48, 49, all the way to 0.55, 56. The increase, it may sound little, but it's really big once you do the calculations.
So basically that means, you know, you get to 0.55, we'll say, that 55% of the weight for the total above ground part is in the grain, right? So when so bringing it down to, like, you know, our listeners, so they fully understand, right? It's 55% of that total above ground biomass would be in the grain. So if we're looking to residue compared to the grain, that's where we can really start impacting some of that.
Yep.
Is there a hypothesis on how high we could potentially get that? Because obviously that'd be the goal, right? Create
95% harvest index.
Well, so I'm thinking back to, like, when we always used to joke about, like, you know, like, you want the corn to cannibalize itself as much as possible, like in farmers speak, right? Like, I want it to convert as much as possible right up until it falls off the cliff and I'm picking it off the ground. So is there a hypothetical number where this is as high as we could get?
We tried to come up with a number, but we didn't finalize the work because soon we realized the maximum number is conditional to some other factors. And one of these factors is what is the grain nitrogen concentration. So it's quite complicated.
Yeah.
But I will get close to what you asked me, Sean. 0.55, I believe, is far from what I think we can achieve with maize.
And is that our average right now is 0.55?
0.55 is what we found from the study and what most of the recent literature suggests. If you look older literature, it's going to be around 0.5. And it is around 0.55. Easily, this can go 0.6 or a little bit more than that.
Can I ask what might be a stupid question?
You can ask me whatever you want.
With short-statured hybrids, and either one of you correct me, there's about 5% less biomass, and it's expressing that energy through the root system. So the harvest index, is that above ground only, or does that include the root mass when you talk about the weight of conversion?
There are two definitions. Usually we refer to above ground biomass when we do the conversion.
Okay.
But the most appropriate from a crop physiology is to include the roots.
Okay.
Who's going to measure roots? That's the question here.
Yeah. No one wants to
Because
do
I was
that.
just thinking by simple reduction in total biomass, if you had identical yields and identical practices and you're only including above ground biomass, you would have increased the harvest index with a short-statured hybrid just because you're not creating as much biomass, right?
Look, this is one way to increase the harvest index, but there is also another ways. You increase the yield more than what you increase the stover. And that way you go to higher biomass, heavier plants, and still you have high harvest index. I like this way.
I had a customer call me that was spraying some short-statured hybrids. He's like, this is awesome, right? Doing like fungicide, and then turns around and he was, I think, a 17-foot tall cord. He's like, I don't like this quite as much. So, boy, we have just abandoned everything we wrote down on this paper.
That's a good indicator of good conversation.
Question around nitrogen concentration. So does nitrogen concentration in the leaves, stalk, and ear impact yield, basically where that plant is partitioning the nitrogen?
Indirectly, yes. You need to have nitrogen concentration in the leaves and in the stalk. Keep in mind two things. The first one, portion of the nitrogen that we have in the leaves and in the stem is going to end up in the grain. During grain filling period, 1/3 of the nitrogen, a little bit less, comes from the leaves and the stems. So you more
1/5.
1/3. I don't remember the numbers now. It's a significant amount. It's not like 5 pounds. It's way more. So the more you have in the stems and the leaves, the better for you.
I'm sure it varies too, because you look at the way hybrids translocate nutrients. You get some that are quick dye and dry, some that stay green.
Exactly.
It probably varies quite a bit, I would think.
It varies a lot with genetics, but it varies way more with the nitrogen fertilizer rate. This is the king there. This is the number one factor by difference that affects the concentration of nitrogen in the leaves and in the stem. And this is why we try to optimize corn at the optimum rate, so we get to this sufficient level of nitrogen in the leaves and in the stem. If we fertilize below, we will not have enough to supply later to the crop.
Is there anything you could learn then post-harvest by going out and querying that? So querying the nitrogen in the leaves, querying the nitrogen in the stock, that then would give you insight into either a particular hybrid's efficiency or your management?
Yes. So you get two types of information shown out of it. First, you can calculate all the efficiencies, agronomic efficiency, physiological efficiency, nitrogen recovery, etc. This is lots of information to explain why and to compare hybrids. There is something else, something that people don't consider a lot, and something that I believe is going to be really important for the future. If you do what you said, measure the nitrogen in the leaves and in the stover after harvest, it's fantastic information to have to know how much nitrogen you have left behind in the stover. And this is going to determine how fast the stover is going to decompose. Really valuable information. Extremely valuable. I tell you that from a crop modeling perspective, knowing what matters the most in the system, this is one of that.
So what kind of impact does it have in breakdown?
I give you two examples. Let's say you have corn, your stover has a CN ratio of 50, and you have another corn and your CN ratio has it's 100, like the episode 100 series. The one with the 50 is going to decompose faster and is going to immobilize way less nitrogen from the soil. The one with the 100 is going to immobilize lots of nitrogen from the soil to break it down. It's the quality. It's what you bring on the table, low quality or high quality.
We have to be careful that we don't just kind of go all over the place, but my mind is thinking about over the last 5 to 6 years, you've seen all these breakdown products, right? The products designed to help stover breakdown. And you'll see somebody say, oh my God, this worked so well, right? And then somebody else like, I saw absolutely no result. Well, if we don't have that baseline, do we have any idea what is existing in the field, right? So even, I'm thinking back to the conversation we had with Connor Sybil at Illinois, where he was just saying some of these results are really variable. Well, that ratio that you're talking about could be playing an even more significant role. So we could be out thinking we're managing residue without even knowing our baseline to start at. Is that?
Exactly. I will not. This is to me is 101. You must measure this. If you want to explain the why, you need to know the CN ratio and you need to know the amount that you leave behind.
And that's going to vary year by year. So it's not like you can do it 1 year and
you know, within the field, that portion with the other portion of the field.
yeah.
Let's remember to ask that question in the management portion, because I'm curious about the practical application of that from an advisor or grower standpoint.
So thinking about and building on, we'll get maybe a little bit more into this with the management portion, is nitrogen concentration. You know, you just got done saying that the nitrogen concentration in the leaf matters in terms of yield. And in the stock, it's good to have not a lot of that in there because that impacts yield. How can we, from a physiology perspective, whether it's timing, rate, is that something we can impact?
Yeah. You know, the answer to this question is conditional to the region. So the answer for Indiana is different from Iowa because of the weather and in Iowa, central Iowa, rate is by far the most important. And this amount, the rate, can affect a lot the concentrations of nutrients, of nitrogen in the plant. A lot. Timing in some years is going to affect, not every year. Not every year.
In a dry year, it's not going to matter.
Is that
right?
driven by the soil, primarily the CEC and the mineralization?
It is more complicated than this. It is the soil moisture as well. Like you put your nitrogen, your second or your third dose, let's say today, and it's not going to rain for the next 10 days. You put it there, the plant cannot use it. Mm-hmm. So it's the timing. You need to know the perfect timing to apply to see the maximum return on investment. And you need to ensure that you have moisture supply for the roots to take up this nitrogen. So it's,
or maybe it rains 13 inches and it all goes away. Yeah.
You're right.
The new fun stuff we're dealing with, yeah.
Oh yeah, we're the new normal. Lots of rain in a few days.
Yeah.
So Sotirios, I'm curious, thinking about, obviously we're in the Corn Belt. We got a lot of corn on corn acres, right? Mm-hmm. What does nitrogen content or concentration look like in the leaves, stalk, roots, just overall nitrogen usage and allocation of nitrogen to different plant parts? What does that look like in corn on corn compared to corn on soy? Is that still the same?
The fractions and the patterns are going to be the same. It's going to be the same. What is going to change between corn and corn soybean is the amount of biomass and the requirement for a little bit more. In terms of concentrations, I don't expect to see significant differences.
Okay.
In terms of amount, if you measure amount of nitrogen in the leaves at R1 stage, you may see something, but not big. Keep in mind something else important. I'm going to go again a little bit outside the equation. Over the years, the big differences that we used to know between corn and corn soybean are disappearing. We used to say 50 pounds more nitrogen in the corn following corn. This gap, the 50, has become 35 and is closing.
So right now you're kind of 35 more pounds needed in corn on corn, and you think that's continuing to reduce?
It is continuing to reduce.
What's the reason for that?
Number one reason, yield, by far. Corn following soybean, it yields more. 10% more, 11% more, 12% more, depending on the year, 5% more. And it's keep going up.
Interesting. That's some good info as we continue. I mean, that's something I guess I hadn't thought of. If we're talking about improving nitrogen use efficiency, even though yield's going up, I didn't think we'd be able to impact. You still got that carbon to nitrogen ratio in corn on corn. Mm-hmm. I know Castellano had some interesting numbers. Looking at residue removal and how much nitrogen we need versus the yield impact in terms of percentage. That's good info.
Could we mitigate the yield delta if we were better at handling the residue? Is the residue the main driver in the yield delta?
It is one of the biggest drivers for the yield delta, the residue. One is, if you remove the residue, probably this gap is gonna disappear totally, or a big portion of it is gonna disappear. And residue is great to have. It's carbon, you have it on the soil, but it comes with pathogens. Mm-hmm. They have a house to stay, go through the winter, right?
Right.
So you cannot have everything in agriculture. You have to pick.
We want it all.
Right.
Good luck with that.
Andrew, you can help me if we're off where we want to head with this. I think we're kind of, so a question around sunlight.
Yeah, that's where I was going.
So how does the amount of sunlight or cloudy and rainy days impact nitrogen assimilation and overall nitrate uptake, or nitrogen uptake, sorry?
So radiation. The more radiation you have, the more the growth of the plant. So as you grow more, you ask for more nitrogen from the soil. The plant is clever. It's not going to take everything that is in the soil. It's going to take as much as needed. And the as much as needed is driven by daily crop growth rate. The number one factor that affects the daily crop growth rate is radiation. We don't want to have 30 megajoules per square meter per day. 25 is sufficient. But once we drop below 15, then is where the rate is going down, and then you don't need much nitrogen.
Yeah. I'm curious from your perspective, with the year we've had and the amount of moisture we've had and the amount of thunderstorms, so cloudy days, how does, I'm thinking about the number of cloudy days impacting plant growth and development from a crop physiology perspective, but I'm also thinking about we actually have moisture. So is this an even trade-off in your mind, or how do you think about that?
Great point. I have it as everything starts with potential production. Potential is defined by radiation, temperature, and genetics, and planting date. And then you start adding the limiting factors. Number one, water. Number two, nitrogen. Number three, pests and diseases. So if you reduce radiation, there is nothing you can do with moisture to compensate. So radiation must be high. It rains. We are in a rain-fed production environment. You never know when it's going to rain. Usually there is a correlation between rainy days and amount of sunlight. The correlation is negative. The more rain days you have, the less radiation you're going to have. Unless you get the rain.
Yeah, in massive piles.
Or at night.
Exactly.
Yeah.
Well, it's really interesting, though, because I'd like you to weigh in on this. One of my good friends and I debate all the time this concept of like GDD versus SDD and kind of like when does heat become bad, right? And we measure a stress degree day when we eclipse a certain daytime and nighttime temperature, right? So then you take this year and you go back a few weeks ago, I'm thinking pre-tassel in central Iowa, and we're sitting there doing math going, okay, at a leaf every 3 to 5 days, we're 5 to 6 leaves away. And I'm like, oh, we're 20 days away from seeing tassels. It was, 90 to 95 degrees. The sun's out, insanely hot every day. And I have seen no indication of stress from plants, none whatsoever. Haven't seen beans flipping over, nothing that you would traditionally say, okay, the physiology of the plant's trying to protect itself from this. So I don't even know if I know what I'm asking, but is when you talk about radiation, if you have adequate moisture and oxygen in the soil, which I think by and large we have that outside of the pockets that are extremely saturated, then that total radiation, I mean, in terms of megajoules, we're probably radically high this year, aren't we, with the amount of clear blue sky days we've had. And so even though we've had an excessive amount of moisture, it's come in small increments.
Yeah.
And it seems like we flew through growth stages. So is that being driven by what you're describing? The radiation is driving that daily growth rate up?
Yes, radiation is the number one driver. In agronomy and in farming, we like to simplify things. We have the GDT calculator, we have another calculator, we count the thermal days, and we say this is when it's going to be flowering or silking, etc. It works, but it's not perfect. Right. That's what we need to acknowledge all the times. It's not 100% perfect. It's going to be 90% of the variability explained. And this is one of the years that may not work as well as we want to work.
Yeah.
The first time I ever heard Andrew on a call.
I still remember this. This is when he realized I was a nerd.
I had never heard the term megajoule before, and I'm like, is this dude making stuff up? What is he even talking about right now? So it's good to know that was a real word. You weren't just trying to sound smart.
That's how we measure it.
But we don't really talk about that, right? When someone wants to know where we're at with growth, we exclusively reference, at least in the industry, growing degree units or GDDs. In research, do you guys use a different calculation for radiation? Do you have a separate factor that helps you?
We use GDD a lot, but in the complex crop growth models that we work, we acknowledge and we have seen that GDD by alone, it does not explain all the variability. there are all sorts of things that can delay or accelerate progression through stages.
It's got a weakness because it doesn't look at the temperature at 24-hour period, right? That's where.
And to build on what Andrew said is we measure the air, we don't measure the leaf. Mm-hmm. And what it matters for the plant is the temperature in the leaf, not in the air. And there are lots of things that are going on within the canopy and the microclimate. And to go further, the temperature within the canopy is different at the top and at the bottom. But still, GDD, one of my favorite tools. I teach that in the class. Yeah. I use it in the models, but I know how far I can go with it.
Sotirios, we've talked about the impact of cloudy days and PAR, just the photosynthetically active radiation. What's your thoughts? I know there's a relationship with plants, especially corn, in the movement of water from the soil to the atmosphere. Mm-hmm. And this is a time where, again, we talk about we've had a lot of sun. With storms comes some clouds, depending on if it's a night versus a day storm. What's that? How do you think about? We actually have moisture around tassel now. That's not the norm here across the Corn Belt, right? A lot of times we're dry. What's the impact of being able to transpire and move water and nutrients through that plant at tassel?
It's the best thing that can happen. At silking, keep the corn happy. Water and nitrogen and sunlight. That's all it needs. It's going to make the job. It's a very good thing. As long as we transpire, there is nothing better than this. We give water, we get CO2. That's how we build biomass. That's how we are going to make the yield.
Yeah. And that's cool. It's something. Again, I've been doing this. I've grown up in Ames. You don't always have this weather at tassel, right? A lot of times we're worried about the silks being viable because of dry conditions or the heat and the impact that heat has on pollen. So it's not. I know we had it last year, but I feel like it's rare to have this much moisture around tassel. And we had the same conversation last year. Going into we have seed set going into that R2, R3 stage where we're setting kernel size. That's dictated by moisture, mm-hmm. right? And so, could we be setting ourselves up again like we did last year to have gigantic kernels? And it's really just about filling those kernels.
Exactly.
So,
there's so many. This has been such a unique year from a weather standpoint. My head is like swirling with and then my mind starts to drift to the field and some of the observations we have of the field. It seems like in the last. Really, since the day of the derecho in 2020. So that's almost 6 years ago now?
5 or
6 years ago. It almost feels like we haven't had a year. We haven't had 2 years in a row with even close to similar weather patterns. So it seems like every year we sit here in like the middle of July. It's like, gosh, I wish I had a frame of reference for what I'm seeing here. But every one of them just seems so radically different than the one before, which, going to your point, is kind of the fun part about being an agronomist, is trying to sort out
an ever-changing
Mother
Nature.
But Andrew, help us kind of, I guess.
Yeah. One of the big things, prepping for this, you got a really impactful paper on modern hybrids versus older era hybrids. But I also read a lot of your work just looking at nitrogen and maybe some of the, we'll say simple but complicated reasonings why we see yield impacting corn on corn versus corn on soybeans. And I read an article of yours just talking about something as simple as density, right? And when we look at the impact that residue has on, I shouldn't say density, emerged plants versus in corn on corn versus soybean plants. So talk to me about what you've seen, the impact of residue in that corn on corn situation. Is that yield penalty that we see with corn on corn, is it nitrogen related, or do you think there's something more in terms of actually emerged plants and plant to plant variability?
It is both and more. And this is the reason why we haven't figured it out yet. It's quite complicated. In 1 year, it's going to be residue impact on soil moisture or soil temperature, and you get some penalty from there. Some other years is going to be residue impacting pathogens and then appear sometime later on. Sometimes is the emergence of the plant and survival of the seedlings. It's so complicated, Andrew. I haven't get my mind around it.
So it's anecdotal, and I have no research to back it up. So the comment that I would make, and I guess I don't even know if this is a question or just a statement. it seems like 20 years ago, we would plant a corn after soybean field, and then we'd plant a corn on corn field. And the only thing we would change in those two systems is we would add what we thought was a supplemental amount of nitrogen to the corn on corn field. Everything else would be identical. And then we would also put a heavier traded package. Today, my observations from some of the growers I work with is some still do it that way. And the penalty seems pretty drastic. There's a known significant yield penalty to doing that. I would also say, Andrew, some of the guys that we work with that treat that corn on corn acre very differently, starter fertilizer, much more aware of planting conditions and timing, some of the changes that have happened in traded technology, the way when they think about it almost as like a completely different management. I've actually seen where across large operations, their corn on corn actually can beat their rotated acres. And so I often sometimes think, if we think about it as a whole system, is sometimes the problem we're trying to make it too simple. We want to just do the exact same thing but run corn on corn versus addressing some of those concerns. If I do a decent job of managing the residue, if I help the plants with emergence, if I recognize the fertility restrictions, it seems like some of those things are almost getting narrower. Is that a fair statement, or is that anecdotal?
It's very fair statement. And when I speak and comment about corn versus corn, soybean, this is kind for the average. I know farmers that they have figured it out. They have absolutely no problem growing corn after corn for many years. They don't see many of these penalties and challenges. They have figured it out. And that's the beauty of agriculture. The recipe to fix that problem is site-specific.
Yeah.
Something that works in your farm probably is not going to work in your farm. You will have to figure it out, Andrew.
Yeah. So one of my, I really started thinking about this question after we spoke with Connor Sybil at the Crop Physiology Day in Illinois. What do we always talk about in corn on corn or high residue scenarios? It's carbon to nitrogen. Mm-hmm. Have you ever looked at or thought about, do other carbon to potassium or carbon to sulfur, do other ratios matter? Is that a thing?
It is a thing. I haven't done much of research over there. I mostly stayed with the nitrogen.
Yeah.
But there are lots of other things matter there.
Yeah. That's something I think we have, some of this stuff probably didn't matter when we were growing 175 bushel corn, but now that the entire corn belt's shooting for 250, 275, I think some of this stuff that maybe we don't know much about, we need to start researching.
Absolutely. And now that I'm thinking about this a little bit more, I have a PhD student working on the topic. She submitted a paper about micronutrient, micro and macronutrient concentrations on the grain. And now she's working on what is going on the stover. And she's comparing old with new hybrids, and also 2 different nitrogen rates and 2 different plant densities. So I'm curious to see these results.
Yeah.
I will get back to you on that.
Yeah, that'll be interesting to see an update, because we got that residue, every bushel of grain comes 44 pounds of residue on average. So, if we continue to increase yield, some of these different ratios might matter quite a bit more.
All I can tell you about the grain and the macronutrients is that the slope that we use to do all the calculations, removal rates, etc., the slope has not changed a lot. It's quite robust because there is a compensation there between yield and then genetics dropping a little bit the nutrient. What we see in nitrogen is applicable to the other nutrients as well. So it's, there is stoichiometry within the plant, and if you do something, you're going to affect zone. It's one element affects the other one. That's how the plant works.
Yeah.
Not surprised. That's kind of expected, right?
Yeah.
It also maybe explains sometimes how we see people try like one thing in large volume and not necessarily get the response they believe they will,
Exactly.
because they're not accounting for the fact that the plant desires balance.
Exactly. That's the secret.
I'm excited about this question, and it'll be fun to know the answer to this and then understand how it affects our management. But in your study of current era hybrids, how do they take up and use nitrogen differently?
They take up more nitrogen. That's the first part. And they distribute the nitrogen differently within the plant. Grain gets the priority. The nitrogen harvest index, which is equivalent to harvest index, and to say that very simple, it's how much of the total nitrogen in the plant, is in the grain, has increased with the year of hybrid release. So there are lots of changes within the plant. I will put it into these two categories: more uptake and more partitioning to the grain.
It would be fascinating when we have the opportunity to interview corn breeders to understand what specifically they're able to identify, right? Because to a certain extent, breeding is plant styles we like that have the output we like, but are they able to identify specific markers, whether it's, measuring that distribution throughout the plant in the breeding process, or how are they able to identify those specific traits that are resulting in that?
Yeah. I want to hear what they're going to say.
I'm really excited about. That's one of our goals, is to spend some time with some corn breeders and kind of understand what are they observing, because that didn't happen by accident, right? It's not just sheer luck. They're obviously looking for that style of.
I will tell you this. I spoke with the breeders because part of the project we had breeders in the team, and I say honestly, we didn't shoot for that. This is something we call it indirect consequence of going after yield.
Yeah.
So you go after yield and you get changes in many things. One of the main things are the two that I mentioned.
So to kind of lay the foundation as we get into the management conversation, you looked at, you have more N taken up in modern hybrids compared to old hybrids, and it's distributed differently. To kind of lay the foundation for the management piece, did you see anything different in vegetative nitrogen uptake compared to the reproductive stage nitrogen uptake?
In terms of breeding didn't do much of an effect during vegetative period. Breeding is taking over during a reproductive period.
Okay.
What we learn is that plant density had a significant effect during vegetative period. And to go that a step back, that's the beauty of interaction in agronomy. We have plant density influence the vegetative period, how much nitrogen they're going to take up, the leaf area index, the light interception, and then you have breeding in the second part, where it changes the partitioning towards more dry matter in the grain and increasing grain filling period and having more photosynthesis of the overall plant. And when you put these two together, you go to the high yield. Mm-hmm. That's really fascinating when something of the highlights of our research.
Yeah. So are we, we'll get into this, dig a little bit deeper as we get into some of the management. My last question, other than nitrate uptake and concentration, doing the research that you did, looking at old hybrids and new hybrids, trying to understand nitrogen uptake and use, nitrogen use efficiency, was there anything else that stood out to you that was just really cool to see or something you didn't expect?
One of the hypotheses was that yield comes with some cost, and the cost will be at the roots. So we invested resources to go and measure roots.
Meaning smaller roots.
Yep. We measure the rooting depth, how fast they grow. We measure the root biomass at the end of the season. And we published 3 papers on the roots and breeding. And what we learned was that there was no penalty when it comes to root carbon, etc. It was a whole plant increase in biomass, root and above ground.
With the newer hybrids.
With the newer hybrids. We also found that plant density had a really significant effect on the root carbon. As you increase the density, you put more into the soil carbon.
Okay.
That was
so. I'm assuming the root mass gets smaller as you increase density, but then you get more allocation of carbon. So root exudates, all that.
Correct. Per plant, the root mass is smaller.
Yeah.
But per unit area, it's larger.
Yeah, because you're putting more plants in there.
exactly.
Yeah, that's tricky when you think about the impact
I
of
know.
30-inch rows versus 20-inch rows. That's good info, though. Yeah.
Before we started recording, you were talking about the importance of doing this and having your research explained and essentially not just sit on a shelf somewhere. Will you comment on that as we finish our science episode? I really appreciated what you were saying, the important part of that. Speak to that, and then we'll talk about management.
Absolutely. Scientists are trained to do research, data analysis, interpretation, publication. We are not trained to go beyond publication. And that's the missing part. We really need to invest resources over there. And I really want to commend what you guys do here. And that's really nice. It's a nice way to give out what we learn over 4 years, 100 experiments within a half an hour episode.
Yeah.
That's the most efficient way to say the story.
It's super important to us because it's amazing how often there's preconceived notions or things that just get said. And, you know, they say if you say it enough times, it becomes true, right?
Yeah.
And so there's those things exist all over agriculture. This is tremendously valuable to us. And it's tremendously valuable to people who are trying to make complicated decisions, economics and agronomics, all those things, especially in the current time we're in. So we like to express gratitude. I'm not sure people understand the volume of work that was done by the people that you talked about in this, but we're incredibly grateful. Thank you for your time today, and look forward to your expertise as we talk about management.
Yeah, I'm really looking forward to see how you take all that information you have and how we can potentially use that to help dealers and growers be more efficient and grow more corn.
Yeah, thank you. I appreciate it.
Thank you.
Sure. As always, thank you for listening. If you like the content Andrew and I are creating, please like and share, give us a 5-star review, and look for us on our social media channels at A Penny Podcast.
Thanks for listening.
Stay curious.
Stay nerdy.